Hi guys, we're going to talk about elements in our first official lecture for bioorganic chemistry. Now we're going to the basics of general chem and we're going to just dive right in. So I'm going to shrink my face so you don't have to see me, but that way you can hear me instead. So when we start talking about elements, elements are pure substances from which all other things are built. These include gold, carbon, aluminum, sulfur, phosphorus, helium, nitrogen, oxygen, hydrogen, just their pure actual elements. Now compounds, on the other hand, like things like water or even glucose, are made up of a combination of elements. So we're just going to talk about the actual elements today. And it will help if you have a copy of the periodic table out that you can kind of work through and look through as we go on. Now, elements are represented as symbols on the periodic table and actually throughout chemistry in general. So they're either one-letter or two-letter symbols, and they'll always start with a capital letter. Now, if you see a symbol that has a capital letter and a lowercase letter, obviously that is one whole thing, like CO is cobalt, Ca is calcium, Al is aluminum, Mg is magnesium. If you see two capital letters close together, those are examples of two elements that might be bonded. So these are just examples of the one-letter ones. So we have carbon, nitrogen, fluorine, and oxygen. So some symbols are named after or done right from the name, like S for sulfur, Al for aluminum. Others, on the other hand, like gold and silver, Au and Ag respectively, are actually based on the Latin name, and that's why and tin would be another one, Sn for tin. So they don't necessarily go together, but it's based on either their Latin name or their common name. So here's the actual periodic table of elements, and I want to spend some time on this because this is important for us to really understand because it can help see a whole bunch of trends. Now, the periodic table of elements is broken down into groups and periods. So groups are these vertical columns here going up and down. We have groups 1 through 18. However, to make it a little easier, we have what we call groups 1A, and then we have the B, or the transition elements. So the transition elements, which are down here, which are technically groups 3 or 3B, through 12 or 2B down here, all of these we really don't use that often. These are realistically the metals, and we consider heavy metals. And as much as we will see them in biochemistry, because they do play a role in enzymes as cofactors, we really don't necessarily use them a lot in our chemical reactions. And they don't always follow by the rules and the trends that we'll use. So we have, and we'll usually go by the groups as the 1A, 2A, okay? Because then we have 3A, 4A, 5A, 6A, 7A, and then 8A. And we're going to go by this notation down here. So when I refer to group 3, I'm realistically referring to group 3A. So this column down here. Now, the periodic table also has periods. In periods, they go across, so these are the rows. So period 1 actually only has two elements. It has hydrogen and helium all the way over here. Then we have group 2, or excuse me, period 2, period 3, period 4, 5, 6, and 7. And as we go across, we are actually growing in size, and our number is increasing. So our number of protons and our number of electrons are increasing as we go across. Now there's different colors on this periodic table. All of the elements that you see that are blue are metals. So anything basically to the left of this little step here, this black line, are metals. Everything to the right of the step, where we see this yellow color, are nonmetals. And there's only one instance of a nonmetal that appears on the left, and that is hydrogen, just because it just acts similar to the others in group 1. And we'll tell you why in a little bit. So our blue are metals, our yellow are nonmetals, and our greens Right on the step are what we call metalloids. It's kind of a combination between the two. Now besides that, we have special groups, and we'll go into them as well. But it's good to know group 1 and group 2. Now group 1 are what we call the alkali metals, and group 2 are the alkaline earth metals. The other special groups we're going to talk about are the halogens. Those are group 7, right here. And then the noble gases, which are group 8. And these are actually unreactive. We don't ever really deal with them, but they have what we call a complete octet or a complete outer shell. So we're going to refer back to them a lot. But that's also why they're considered the noble gases. So again, we have metals in blue, nonmetals in yellow, metalloids in green, and the step kind of divides them. So groups contain elements with similar properties, and they're the vertical columns, okay? Like group 1, group 2, group 3, all the way to group 8. And periods are rows of elements, okay? And we have period 1 through 7 on the periodic table. You will on a quiz, and you will on your homework, and I believe you will also on the exam, have to be able to locate things using the periodic table. Like I will ask you, what element is in group 2, period 4? And in this case, you're going to look on your periodic table, find group 2, and then count down to period 4. Now don't just start counting at the top. Remember, you have to start with hydrogen as period 1. So you'd have 1, 2, 3, 4, and that would be calcium, okay? Group 2, period 4. There is technically no period 1. So let's go with those fancy groups first, and let's talk about the alkali metals. So for alkali metals, these are the ones that are in group 1A or group 1. These include lithium, sodium, potassium, rubium, and cesium. And what's neat about these is their reactivity increases from top to bottom, basically meaning the most reactive is lithium, or excuse me, the least reactive is lithium, the most reactive is cesium. And you've probably heard of cesium before, can be used in nuclear reactions. And why lithium is really not reactive as much is it really deals with the atomic structure. And we'll talk about it, but the atomic structure, remember we have a nucleus, and inside that nucleus we have protons and neutrons. And floating around that are going to be our electrons. Now, opposites attract for opposite charges. Now, since the electrons are attracted, which is a negative, attracted to the positive of the protons, because they're so close together, they're strongly attracted to each other and they're holding in. So reactivity means the propensity for an element to really get into a chemical reaction and change and form something new. And you have to give or take some electrons to do that. And the electrons are so closely attached to that positive nucleus down here that they're not that reactive. However, with cesium, they're so far out because the element is big. So we have 55 total electrons, and we have shells that range from 2 and then subsequent 8 and 8 and 8 and after that. So 55 is really far away from that positive center. So those outer electrons are really easy to pick off, and that's why they're more reactive. If we talk about halogens, halogens on the other end are kind of opposite of the alkali metals. These are in group 7 or group 17, so 7A. These include fluorine, chlorine, bromine, iodine, okay? Right over here. Those are the real 4 that we're going to be using. And fluorine and chlorine are highly reactive, with fluorine being the most reactive at the top. And this kind of makes sense because if we think of things in group 7, they're going to have a total of 7 outer electrons in their outermost shell, and they want to get to a complete 8. And so there's going to be a real strong pull to fill in that gap. And because that center that positive center is really exposed, it can pull in another electron very strongly. Or if we go further out, like an iodine, it's less reactive because that center is shielded by so many other electrons, it's harder to pull in another one. And I'm sure I'll show you some diagrams to make it a little bit easier. Now, we're going to talk about noble gases. That's our group 8 or group 18. These include helium, neon, argon, krypton, xenon, and radon. These are non-reactive, and we seldom find them in combination with any other elements because they have a complete outer octet. They just don't like reacting with anything. A cool little bit of trivia for you. Helium, technically there is a shortage of helium, and it is a non-renewable resource, so we are running out of it. Little did you know. And radon, Ra, is actually a radioactive gas, and radon does seep from the ground. Usually a lot of houses around here or in the US have what we call radon mitigation. And radon itself is the #1 cause of lung cancer right after smoking. So I believe it's every either January or February is radon month to kind of promote and talk about radon and how it really does affect human health, specifically lung health, being the #1 cause of lung cancer right after smoking. So with those being said, let's really talk about, again, metals, nonmetals, and metalloids. So we're looking at that step on the periodic table. Right here, this would be group 3. And metals are in blue. They're always to the left of the step, minus hydrogen, which would be up here. Nonmetals are yellow and always to the right of the step. And then we have our metalloids, in between, and those are green. So metals are shiny, ductile. They're really good conductors of heat and electricity. Nonmetals, on the other hand, are not especially shiny, ductile, or malleable, and they're really poor conductors of heat and electricity. They're usually brittle. Metalloids are kind of a combination. They're in between, so they're better conductors than metals, but not as good as other metals. So we call metalloids semiconductors, and they're usually really good at insulating, and they're insulators. But what's really important and what I really want you to know are what we call the major elements that are essential to health. So specifically, you need to know the ones in red. These are the major elements, and then we have the macro elements and then the micro elements. So the major elements are these ones in red, so hydrogen, carbon, nitrogen, and oxygen. Your body is basically made up of those 4 elements and hardly anything else. You have a few bits of other things, but mainly you are hydrogen, carbon, nitrogen, and oxygen, the bulk of the body. Now the next set that's really important to know, so I want you to know what's in red, and I also want you to know what's in blue. What's in blue are what we call the macronutrients. Okay, these you actually need in quite a bit amount too. So these include sodium, magnesium, calcium, potassium. And we can think of the sodium-potassium pump as one. Calcium is exceedingly important, and we think about muscle contraction with calcium. That's what I think. Go back to A&P and think about how that sarcolemma works. So you have your muscle fiber and you have the sarcolemma, and when the sarcolemma releases a flow of calcium ions, it causes the actin and myosin heads, remember, to bind in and lock in to tighten the muscle. So calcium is helping with that muscle fiber. Okay. You also have in the other blue that we can't forget phosphorus, sulfur, and chlorine. Now sulfur we use in disulfide bonds, very important when we talk about DNA and in proteins too, and when we talk about protein folding. And phosphorus in particular, where people don't really think about it, is ATP, or energy, okay? Adenosine triphosphate has phosphorus in it. So those are the big ones. And then what we call our micronutrients, these we only need in trace amounts. And these are really the metals, okay? We have cobalt, chromium, manganese, iron, copper, and zinc. And these four right over here, Fe, Co, Cu, and Zn, we will see a lot of that when we start talking about electron transports. These metal ions are really good as cofactors, and they help us, and they help to move electrons and shuffle it through with impulses. So we'll get back to that. And iron obviously is very important when we think about hemoglobin and even myoglobin, so bonding to oxygen. So with that said, let's review the atom like I was talking about before. And the atom has its center, which is known as a nucleus. It is filled with what we call neutrons and protons. Now, neutrons are neutral and protons have a positive charge. And then surrounding those, what orbits the nucleus are electrons. And electrons are going to orbit the nucleus in shells, as we say. And the first shell is going to be filled with 2 electrons, and the subsequent shells later on will be filled with up to 8. So when we think about these subatomic particles, it's important to note the charge. Protons being positive, electrons being negative, and neutrons having no charges. And just in basic physics, like you've learned before, positive or like charges repel each other. So 2 positive charges will repel, 2 negative charges repel. But unlike charges attract each other. A positive and a negative will come together and attract. Same thing if you're like playing with a magnet. So there we are again, you have the structure of the atom, we don't want to forget about it. And then we're looking at our electrical charges, positive for proton, negative for electron, neutral for neutron. And then the important part is also when we talk about mass, protons and neutrons are about 1 AMU atomic mass unit, and electrons are 0.0055, basically nothing. They are massless, they're just a little floating charge. And actually, we usually call them charge clouds that just float around. So these learning checks you'll see throughout all of my PowerPoints coming up, but they're a good idea to just stop and try to answer these. And it gives you a baseline of what type of questions I might ask from a quiz or an exam. So if I ask you to identify each statement, describe it as a proton, neutron, or electron. The first one is something that is found outside the nucleus. So if we think about that one, if it's outside the nucleus, it would be an electron. If it has a positive charge, this would be a proton. If it is neutral, it has no charge, that's a neutron, and found inside the nucleus. Don't be tripped up here, there are actually 2, protons and neutrons. When we look at that periodic table, we also notice that there's a number usually on top of the symbol. So the symbol again is the element, and the number on top, this is important, is equal to the number of protons in an atom. So as a hint, as we go through all these PowerPoints, anytime you see anything in red, or that is bolded, or is repeated numerous times, those are important concepts that I want you to know. So I really want you to know that the atomic number is equal to the number of protons. Now, because all atoms are inherently neutral, the number of protons is always equal to the number of electrons. So let's go on to a learning check. What I want to do now is hopefully you have your periodic table available. If not, now would be the time to grab one. I want you to state the number of protons in each of the following. And remember, the protons are the atomic number, the number that comes above the symbol in the periodic table. So the first one is nitrogen. Its symbol is N, and it has a total of 7 protons. Carbon, right next door, its symbol is C, and it has a total of 6 electrons. If you're looking for barium, you need to look for this element that is Ba. And that one has a total of 56 protons. So if we want to know what the number of electrons in an atom are, we have to know that all atoms are inherently neutral. That means the number of positive charges equals the number of negative charges. So the number of protons will always equal the number of electrons. So in an example, if we look at an atom of aluminum, aluminum has 13 protons, and therefore it'll have 13 electrons. So just to give you an idea again, we're looking at our atomic models, kind of just showing you, looking over here, we have our lithium, right here, that's a metal, and it has 3 total protons, which means it'll have 3 electrons floating around outside. Now carbon up top, okay, carbon is in group 4, well 4A or 14. It has a total of 6 protons. So it'll have 6 protons and it'll have 6 electrons floating on the outside. When we talk about mass number is the number on the bottom of that periodic table, okay, below the element symbol. And the mass number represents the number of subatomic particles in the nucleus. And usually, I know it's never a full regular number. There's usually a decimal point. And that's because you can vary in the number of neutrons that you have. And those are actually called isotopes. And that's more of a gen chem concept. But like if we talk about carbon and carbon dating, and there's various types of carbon, we're just talking about the number of protons, the number of neutrons in the nucleus, and that's how it changes. And so this is how you get that like 12.01011. So carbon would normally have a total of 6 protons, and it would have normally 6 neutrons. However, there are some that have like C12, C14, where you have more. There's even like a carbon-20, where you have more neutrons present. So the mass number in general represents the number of our neutrons and protons, okay? And don't worry about the decimal point. That's just because we have a variance in the number of neutrons possible. So if you're looking at the periodic table, and we're going to do another learning check now, I have an atom that has a total of 14 protons and 20 neutrons. I want to know what the atomic number is, what the mass number will be, and what element it represents. So the first thing we'll look at is the atomic number. Remember, the atomic number is the number of protons. So the atomic number for this case would be 14. Now the mass number is the number of protons and neutrons put together. So let's just combine 14 plus 20. That should get us 34. And when we're asking what element it is, remember the element is dictated by the number of protons. So we're looking for an element that has atomic number 14. And on your periodic table, if you're looking at atomic number 14, that should get you to Si, or silicon. So this is a key concept, and we brought it up earlier when I was talking about reactivity of alkali metals and then also the halogens. But overall, electrons determine the physical properties and the chemical properties of all the elements. And they actually really deal with what happens when we talk about chemical reactions. So in this case, we have an element of sodium. Now sodium has a total of 11 protons. So the first shell always fills 2 protons, okay? And then every subsequent electron shell after that fills up to a total of 8. So we have 2, and now we're going to do 8 around the outside. So 8 is the next shell. That makes us 10, and we still have 1 more because Sodium has 11 protons, therefore it has 11 electrons. We have 1 left on the very outside. Now that 1 on the outside and in this last outermost shell is known as a valence electron. What's really cool if you're looking at your periodic table is that sodium falls in what we call group 1. Group 1 has 1 valence electron, and there it is. And because of that, it is, remember we're talking about reactivity here, the level of shielding. This will usually give up that 1, so it has a complete octet to form a reaction. So when we look at those electron energy levels, every time we increase and we go up higher and higher, so the outermost electrons are the ones that have the most energy, okay? So the farther away from the nucleus we get, the more energy we have, and the more electrons they can hold, and therefore the more reactivity we might have eventually. So the furthest away electrons in that outermost shell are known as valence electrons. And that's really the key concept I want you to know, is that the outermost shell of electrons are known as valence electrons. Okay? And that the valence electrons are going to eventually equal what we call the group number. So valence electrons are very important, and you will see this concept come back on a quiz, and you'll also see this concept come back on the exam. So I would like you to know that valence electrons determine the chemical properties, and these are the electrons in the outermost highest energy level, and they are related to the group number. So if the group number is 5, that means every element in that group has 5 valence electrons, or that outermost shell. Okay. Now, in our total number of valence electrons, we can be up to 8 total, which is an octet. And don't really worry about these numbers down here. This is just if we're remembering electron filling. We have s orbitals, p orbitals, and d orbitals, and f eventually if we get up high. But these are just the level. Level 1 only holds 2 electrons. The second shell holds a total of 8, so here's the 2 plus 6. And then the third shell will hold another 8. It's another s and p orbital, okay? So if we're adding up 2 plus 3, that means we have 5. But you don't have to worry about this part. I just want you to know that everything in group 5 has 5 valence electrons. So all the elements, okay, that are in the same group, so that same vertical column, have the same number of outer electrons. So if we look at elements in group 2, okay, 2A or group 2, they all have 2 valence electrons. So this includes beryllium, magnesium, calcium, strontium, they all have 2. So here we are, we're just looking, these are our group numbers up top. Remember I said we're going to go with the 1A, 2A, 3A is how we usually talk. We're skipping over the transition metals. Here are the numbers if you're counting across fully to 18. So everything in group 1 are alkali metals, all have 1 outer valence electron. So you can kind of see it with this little dot here. Okay, hydrogen, lithium, sodium, potassium all have 1. Everything in group 2 has 2 valence electrons. Everything in group 3 has 3 valence electrons, so like aluminum, gallium. Everything in group 4, such as carbon and silicon, all have 4 valence electrons. Everything in group 5, nitrogen and phosphorus, have 5. Everything in group 6, like oxygen and sulfur, have 6. Everything in group 7, so fluorine, chlorine, bromine, and iodine, will all have 7. And then we have our noble gases here. Okay, 7 was our halogens. Here are our noble gases, and they all have 8. And 8 is a complete octet. So we have neon, argon, krypton. The only one that doesn't have 8 is helium, and that's because it fills its first outer shell, which just fills up at 2, and that's considered complete. Okay, so our noble gases are our complete shells. So using your periodic table, let's look at the following, and I want you to tell me how many valence electrons are in each of the following. So O stands for oxygen. Oxygen itself is in group 6, so it will have 6 valence electrons. If we're looking for Al, Al is aluminum. Aluminum is in group 3, so it will have 3 valence electrons. And if we're looking at chlorine, Cl, chlorine is all the way in group 7. It is a halogen. So everything in group 7 has 7 valence electrons. If we look the other way and I ask you to check on calcium, so calcium, its symbol would be Ca, and that would be in group 2. So it would have 2 valence electrons. Anything in group 6, again, this would have 6, so we're thinking of things like oxygen. And tin overall, its symbol is Sn, and that would be in group 4. So it would have 4 valence electrons. Now, instead of just saying the number and drawing however many we have, like could you imagine drawing barium with 56? That's a lot. And considering it's only the valence electrons that actually interact and cause the chemical reactions, what we do is we draw them, and we only draw the valence electrons. We don't actually draw any of the other inner ones. So we use what we call electron-dot symbols. And electron-dot symbols indicate just the number of valence electrons. And we fill them around. What we do, you would write the symbol. So for magnesium, we would write Mg. And magnesium is in group 2, so it has 2 overall dots. And we would just put them around. The one thing you won't do is you don't fill them close together. So when we start filling these, you have to imagine that there's 8 spaces around Mg. Draw a box, okay? And we fill them singly first. And this deals with, realistically, going back to Gen Chem, how electrons fill in shells. They spin what we call in opposite direction. One spins up and one spins down. And you fill them singly first, and then they pair up. So they like to be alone, and then we can pair them. So it doesn't matter where you draw those 2 dots, as long as they're not together, you're okay. Once we hit 4 dots and we go past 4, so anything for group 5, 6, or 7, then we're going to double up. But if it's anything from 4 and below, we just put them in their own individual spot. So if we're looking for anything for group 1 to 4, we use single dots and we spread them around. And anything from group 5 to 7, obviously, will pair up. And just to show you again, and just to hit this concept home, because this is really the important one, the group number equals the number of valence electrons. So anything in group 2 will have 2 valence electrons. And you will be tested on this concept. So just remember that the group number equals the number of valence electrons. So if I show you a symbol and just give you X with 1 dot, what could this be an element of? So which one could this be? And the answer would be anything in group 1. So it could be sodium, it could be potassium, just anything in group 1 that would have 1 valence electron. If I showed you number 2, if we're counting for number 2 has a total of 5 valence electrons. And so this would be anything in group 5. And that's the end. So guys, If you have any questions, please let me know. Obviously, make sure to attend the Zoom sessions we have this week. And I'll also put up some problem videos about how to really draw those electron-dot figures. And we'll just run through some. But try the homework, and then if you have any questions, shoot me an email. You can shoot me a text. Heck, you can even call me. Okay, thanks. Bye.